Good afternoon, and thank you for joining us. Today's a little bit of a different episode for us here. We have a special guest who came in from the Space Weather Prediction Center, and he's going to tell us a little bit about what goes on there. So welcome our guest here. We have Shawn Dahl. Tell us a little bit about yourself, Shawn.
Hi, Nathan. Thanks for having me on the show. Yeah, I am currently the service coordinator at the Space Weather Prediction Center. The Space Weather Prediction Center is a NOAA National Weather Service national center, and our focus is the sun and space weather. I've been here about 10 years now as a forecaster, and I've been in this current role as service coordinator for the last 2 years. And service coordinator, what I do is what we're doing today. Education outreach, talk with the press and the media when events are happening, or help educate them more about space weather, work with core partners and decision makers that need space weather information because of all the impacts this can have on our technology. And that's just among a few of those things.
Perfect. So for someone who doesn't really know what the Space Weather Prediction is or what it does, can you kind of fill us in on the Space Weather Prediction Center's role?
Sure. And from here on out, the Space Weather Prediction Center, SWPC for short, I'm just going to call SWPC. So we here at SWPC, what we do is a 24-hour, 7-day-a-week operation in the forecaster section. The rest of the center has others like scientists and researchers, some college and contractor folks that help us out with the mission here, which is to understand and predict space weather better because of the impacts this can have upon our technology. So as a 24-hour, 7-day-a-week operation, most of us have a meteorology background in some capacity, but I've also gained a lot of this space weather background. And space weather is really about what's taking place in the sun and in that huge vacuum of space between the sun and the earth, and ultimately at, here, and around our planet. Because it not only can affect satellites and space missions and space launch that we think of in outer space, but can affect our technologies like electric power, GPS systems, aviation, and more.
Perfect. So we've seen a lot of limelight and kind of highlights on the Northern Lights recently. We just had an event here in Green Bay, Wisconsin that everybody got involved in. They love seeing it. Can you give us a brief overview on what kind of starts that whole Northern Lights cycle?
Sure, Nathan. There's a lot that goes into that, into the aurora and its development and what happens. So we'll focus on a couple of things here. One is the sun can have something happen at any time in its solar cycle. A solar cycle is roughly an 11-year period of time where the sun goes from a minimum of activity to a maximum of activity and back down to a minimum. So in between there, during the solar cycle, and the one we're currently in is number 25, we're in and around solar maximum right now. During solar maximum, some extra things tend to happen a little bit more frequently. One of these is something not only beyond sunspot developments, and sunspots are these giant dark artifacts that show up in the sun as a reflection of strong magnetic fields that puncture through the surface of the sun, and they kind of inhibit the normal distribution of light and heat. So they show up as these darker, cooler areas. But the interesting thing about them is they're very strong localized magnetic fields. And because they can be so intense, they also, because of the sun's rotation, every 27 days on average, the sun makes a rotation, but the equator is rotating 10 days faster than the polar regions. Because of that, the magnetic field gets stretched and twisted and really discombobulated. So you get these very strong, localized, twisted up magnetic fields that can be like a rubber band getting over twisted and stretched out, and eventually energy's got to give. And when it does, it can result in a number of different solar phenomena, one of which, called the coronal mass ejection, or a CME for short, is what led to the aurora light show we just saw in and around Veterans Day.
So with these CMAs, how quickly can we see these conditions change as they start to head towards Earth?
Well, the fascinating thing about CMEs is we never know when a CME is going to happen. We can predict the probability that a solar flare will happen and how strong it might get to based off our NOAA space weather scales, this 1 through 5 scale. Same with something called a solar radiation storm, a more frightening sounding term, among other things. But coronal mass ejections, we just don't know when they're going to happen. But what we do predict is that what's called a geomagnetic storm. A geomagnetic storm, think of it as a magnetic disturbance here at Earth because of interactions in the solar wind and Earth's own protective magnetic field. And when those connections become disturbed and intensified and favorable, we get all this interaction of solar wind that interacts with Earth's magnetic field, and it causes all the electrons that already exist in Earth's magnetic field to go flinging into the polar regions, and they collide with Earth's own molecules, and that's what leads to things called the Northern Lights. But CMEs, even though we can't predict them, we kind of know signs to look for where we can get a little more concerned that they might happen. And fortunately, we have instruments in space now called a coronagraph, which sees CMEs for us. So think of a total solar eclipse, what that looks like. That's what these instruments do. They make an artificial eclipse, and we can watch for these expanding bulbs of solar material that have these invisible magnetic fields within them.
Perfect. So you talked a little bit about the timing and how you don't really see it come up. Now, when we're talking about, other solar storm forecasts, what are some other things you guys do that you have a little bit more advancement on for timing?
Yeah, the solar flares, we can predict those. Solar flares are sudden bursts of electromagnetic energy that cover up much of the spectrum that we measure, but we measure them in X-ray levels. And the reason we do that is because that gives us an idea of the intensity and what's happening in our outer atmosphere that shields us all from these harmful events, because they can affect some of our technologies like radio communications on some certain bands from working properly. And we can predict those out to 3 days in advance with pretty good reliability, although we never know exactly when a solar flare is going to happen either. So therefore, we cannot warn upon them. We can only predict the probability that they'll happen based off that scale, but we cannot warn on them. Solar radiation storms, so that was bursts of energy, speed of light stuff. We see it, the impact is already on the sunlit side of Earth's atmosphere. A solar radiation storm is particles, but they can be almost speed of light, but not quite. So we do have a little bit of warning notice here. And those can travel and get here as fast as 15 to 20 minutes, and sometimes it can be 24 hours or more, depending on where they happen on the sun and just how strong they are. And then the geomagnetic storms, we can predict those out to 3 days or further in advance as well, depending on what the phenomena is that's occurring and causing them. But generally, CMEs, they can arrive here in as fast as 18 hours, maybe as quick as 15, but usually it's anywhere from 2 to 4 days.
For that geomagnetic storm, you were talking about the scale of, G3, G4, G5. What does the grading process look for that, and how do you guys lead up to, we're going to scale it at this point?
Yeah, just like in regular meteorology that we've all, delved in, including yourself as a profession, we have all sorts of indices. And one of the indices that we use, call it an index, is something called the KP index. It's a 0 through 9 number. And each of those numbers, with the exception of 9, is divided into 3. So you can have a low end, a middle end, and a high end. So you can have a 2M, a 2Z, or a 2P, for instance. When you get to a 5 on that KP index, now we give it NOAA Space Weather Scale attribution. So that becomes a G1 storm. And it works this way until we get to G4. A G4 is all the KP8 levels, as well as a KP of 9M. The top of our index is a KP of 9Z. It doesn't measure any higher than that. So you can have a KP of 9Z that's here, at my head level, or a KP of 9Z that's several stories above my head. That would be a G5. And that's how that scale normally works. It was created to kind of be relatable to something like the hurricane scale. So we have levels that are below NOAA Space Weather Scales that are important, that we're warning about and talking with core customers and key partners about. But not until we get to that level, like going from deadly tropical storm force winds to hurricane winds, something similar here. We can have important measures, but now we reach this level, we just give it NOAA Space Weather Scale attribution.
Perfect. So we've seen this year, and I even seen it last year when I was still in Buffalo, New York. We had seen a lot of strong geomagnetic storms. Now, it seems like we're talking a lot more about them. Is it because they're just becoming a lot more prominent? And some of these ones that we are seeing that are stronger, how rare are these?
It depends on the level. The level that we're seeing, the aurora that we're at, that's much more rare. Usually it takes a G4 or a G5 to get to the levels where most of the country is seeing the northern lights in some way or other. And that's happened several times this year. We've hit G4, at least 4 or 5 times now in the last year and a half. G5 we've hit once, and that was in May of last year. That's the one where the aurora was seen way further south than usual because everything came together properly for that to happen. But G4s themselves are really quite rare. If we're up in Wisconsin or the upper Northeast, you really need a good G3 to be able to cover up the entire state or most of the upper part of New England area, if you will, or Washington State. A G4 will get you started going further south. But the fortunate thing about being in Wisconsin is you can see them even in northern Wisconsin with just the G1 when things are favorable, because you're very geomagnetically favorable. Earth's magnetic field Fortunately for people who want to see the aurora, unfortunately for people like transmission operators that control the electric power, there's a dip in Earth's magnetic field that makes the aurora and geomagnetic activity to be happen a little bit more than you'd think further southward because of that trough or that southern dip across the northern part of the United States.
So do the visual effects of this, maybe, color and whatnot, change based on where you're located? Like
To
as far
some
as like
extent,
in the US or yeah.
right, Nathan, to some extent of how you see it or how you capture it on your digital technology, because what's
Mhm.
happening is this flood of electrons that are interacting with Earth's molecules that exist up in the atmosphere. You get normally your greens because it's interacting with the state of oxygen that's up there. You start to get reds that are at a higher altitude with a different state of oxygen that's up there. If you're fortunate enough during a very, very severe extreme storm to see blues and purples, now we're talking about nitrogen molecules that are getting interacted with. But what's happening today, and this is why I think people are noticing this, and there's so much more about space weather and people becoming intrigued, is because we're looking up now. There's been a lot that's happened, right? Comets that have been seen with your naked eye, total solar eclipses across the country, big sections of the populated part of the country. And the aurora shows have really picked up, and they've happened at pretty favorable times when people are out and about in the evening are willing to do it because they learn more about it. And more importantly, their digital technologies help. So even if you don't see visually the aurora, people are capturing these brilliant reds on their phones and a lot of these pictures much further south than we'd expect the aurora to be seen visually because of digital technology. So even if people can't see it and they think, why am I not seeing it? I should, everything's coming together. Try your phone or your digital technology. It very well could be there right in front of you.
Right. And light pollution also plays a big part in this, correct? Depending where you are, kind of need to be in a spot where that light pollution's a bit lower.
Yeah, exactly. Especially for the normal aurora shows that aren't so dramatically strong and intense that they're getting over your head. Yeah, you want to have pretty unlight polluted skies to your north, to that whole northeast through northwest sector. And it's always helpful not to have a moon in view during the night. Now, this time of year, it's pretty low in the sky, so it shouldn't be much of a factor, even if it's near a full moon, but it still does kind of flood out the sky with fainter aurora chances.
Perfect. Well, on this show, we do take a few breaks. So we're going to take 1 minute and we will be right back and we'll talk a little bit more on what Shawn has to say. Alrighty, so we are back after that quick short break. Now, we're going to hop right back into this. So, we talked a little bit about the technology and infrastructure impacts it might have. So, beyond pretty colors that we see with these northern lights, what potential risk do solar storms pose to satellites and some of our other communication systems that we do rely on?
Yeah, thanks for asking that, Nathan, because that's very important. I mean, that's why we exist here as a national center. That is why we do what we do. We don't predict the aurora. So if people are wondering about that, we don't do it because it really itself isn't of a major consequence. Yes, the aurora can impact some technology as well, but basically just communications on certain radio bands. But what space weather generally can impact in some of these more significant activities is anything from the aviation, from potential radiation exposure to air crews and or passengers during the more severe or extreme solar radiation storms. GPS systems can become completely out of whack, especially precision GPS systems. So those oil drilling or fracking industries that are trying to drill deep down into the core of the earth to extract materials,
Mhm.
they have to be accurate within a centimeter all the way down, and that can't happen. So they'll suspend those operations during some of these events. Aviation farmers, they're dramatically impacted because their GPS systems won't work. We saw that in May where it was a billion dollar loss to the agricultural industry alone because of the delay in farming, because we had no idea how reliant farmers are on GPS systems
Right.
today. So we're learning more and more. Aviation was suspending flights with the storm we just had around Veterans Day. 33 flights were canceled due to a pretty notable solar radiation storm we had going on at the same time. Other flights were rerouted. The power grid, the electric power grid of this country in southern Canada, we communicate with them directly. When we just get to a 3 on our scale, a G3, a strong event, we are picking up a phone and we're making a hotline call to basically that entire bulk electrical system that provides power throughout our country to let them know, because these can cause currents to happen on those high voltage transmission lines. that can overheat transformers. For one, they're the wrong current, and the other part, they just make things out of phase. To make a long story short, they have to mitigate and manage those currents that develop on there from these storms, and they can get quite notable. And there can even begin to be occasional isolated small blackouts, perhaps even when we get to that G5 level, maybe even a little underneath, depending on how dramatic things are. But normally, since we communicate with entities like that, from satellites to GPS to NASA for the astronauts on the space station, and when we go back to the moon, those astronauts are our responsibility when it comes to their safety for radiation storms. We warn in advance. We provide decision support, letting them know exactly what's happening. We'll do this even with the emergency management sector through FEMA and down through some state watch centers, because they all want to know and need to know what's the risk that they're going to have an impact to their electric power. They could knock power out for people for days, not just over a section of a city block, but we're talking states in coverage if something like that were to happen.
Okay.
And then the satellites that rely on so much more. So that's what we really focus on here at the center.
So we're talking a little bit on, what technology is affected. What technology do you guys mainly use when you're forecasting for these things? I mean, what do you guys have your hands on?
Yeah, well, we have satellites in space, which is pretty cool. I mean, we all do that in meteorology with the GOES satellites to take pictures of clouds and now lightning and other things for us. We have satellites that are looking at the sun. So we don't have to worry about atmosphere and a cloudy day. We're up there and we're able to see the sun continually. Now, those instruments cost a lot of money to get up there. And so we don't have a lot of them. That's part of our problem. We're covering a distance of 93 million miles from Earth to the sun. So our main satellite package really starts to begin where we have a few satellites about 1 million miles from Earth directly between the sun and the Earth. And they're measuring that solar wind and the magnetic fields embedded in the solar wind force. We have a coronagraph out there as well. That's a research satellite. Unfortunately, it means we don't have control over it operationally, so we can lose it from time to time because NASA may need to track some probe that's out by an asteroid, for instance, but that's taking pictures that help us identify coronal mass ejections. However, the SWFL L1 mission, the space weather follow-on, will be in position in January, and it has a compact coronagraph on it that is ours. It's operational. So it'll be a new replacement package for measuring the solar wind and giving us imagery of coronagraph imagery every 15 minutes. That coupled with the one here near Earth will give us an updated image every 7.5 minutes. That's a huge leap forward for us. And then finally, there's also some observatories on the ground. We have a very key relationship with my old profession of 22 years, the United States Air Force, and now Space Force, where they have a fleet of radio telescopes, because some significant activity can happen on any radio channel as well from time to time. They can really be disruptive, like it was in December of 2023 when traffic control and pilots could not talk to each other across much of the country. And it became very concerning where they almost had to shut down airspace.
Wow. So with some of this technology, I'm sure you're getting a lot of different data points in. Is there anything within those data points that you guys see that really kind of excites you or alarms you when you start to see it? Like, what is kind of the point in some of that data that you're collecting?
Yeah, when we, solar flares are a pretty routine thing. The stronger they get, the less routine they become, but that's pretty standard and a more frequent event. Even during solar minimum, we can have flares. Solar radiation storms, on the other hand, these energetic particles in the form of protons, that gets a little more excitable when we see those. Not the routine ones that our scale is based off on, the S scale as we call it, because that's measuring only one energy level. There's other energy levels. Those higher energy levels, they become more concerning. So when we have an event like we had just around the Veterans Day storm, there was also a pretty significant solar radiation storm that happened. And those higher energy levels that we see less of, even during good S-level activity, became highly enhanced, so much so that we talked about the flights that were canceled. We're going back to the moon. So this is new territory for us, right? The Artemis 2 mission. We're going to have 2 forecasters deployed to Houston Mission Control during that mission in February, should it stay on time. And they're going to be responsible as in-place decision support, talking about radiation storm chances and changes in the forecast for those astronauts. And then again, when we walk on the moon a year or so later. So when we see that kind of thing happen, it gets a little more excitable because it's so much more rare. And then CMEs, we see those quite routinely as well. But when you start to get magnetic fields that are 12 to 15 times stronger than what's normal in space, okay, that's extremely rare. And that gets us a little bit more excited about, are we going to have one of these potentially catastrophic geomagnetic storms, or is this going to be just a one to really pay more attention to for mitigation purposes?
Perfect. So you talk a little bit on us going to the moon. It's a big step. Now, can you give us any insight on some of the new technology or upcoming ideas that might improve some of that aurora forecasting? Does being on the moon impact that at all?
Being on the moon does not, but because of the
Okay.
lead up to and needing the things that we need to help the astronauts and protect their safety, there's been new and better calibrated instruments that have been added to some of the latest spacecraft that are measuring things for us. For example, GOES 19 has a much better sensor on it. It can measure some higher energy ions and what we call alpha particles, and that's important as well for human health in space. We didn't have that in decades prior, but we do now. So that'll help us. That also helps us with our radiation storm forecast because we can see earlier indications. SWFL L1 is going to have a particle sensor on it. And that's awesome because we can see clues and signs not only of a potential radiation storm that's at our doorstep, but also of a CME moving through space. So when there's times where we're not sure, hey, where's the CME? We're not seeing it show up at that 1 million mile point yet, but we can see these particles rising. And that tells us that, hey, there is something moving through space. So we just need to wait and be patient.
Perfect. Well, thank you very much. We're going to take one more break, and then when we come back, we're going to talk a little bit about public safety and communication and what role the Space Weather Prediction Center plays in that. We'll be right back. And we are back once again after that short break. So we're going to talk a little bit about public safety. So you guys play a very big role in that. We reached out to your guys' your website and whatnot when we were talking about the auroras and the effects that the geomagnetic storm may have had. So what can you tell us about the alerts or warnings that you guys issue to keep the public informed?
Yeah, thanks for that again, Nathan. That's an important question because most people should be familiar with National Weather Service warning and watches and what that distinction means, right? What a tornado warning is opposed to a watch. Well, we have watches and warnings as well, and something also called alerts. So a watch we put out only for geomagnetic storm activity. Why? Because that can be 1 to 3 days in advance that we can put those watches out for, and they don't happen that routinely. We do warnings up through that G3 level. We stop at G3, though. We just call it a KPS7 or a G3 or higher warning. Why? Because activity can escalate so quickly. So we just kind of stop it there. And then we alert. Anytime we hit we started at KP of 4, so below a G1, we send out an alert. And this happens every 3 hours that we start to issue them for the G1 when we get to G1 levels at KP of 5. Every new level we reach every 3 hours because the way of measuring these kind of resets itself every 3 hours. Then we'll send out an alert at the new level. For radiation storms, we do a warning because we can have a little bit of advance notice here. And that'll be one warning, and that's basically for an S1 or greater event. But then we'll alert at every single level that we make up that scale. And then for solar flares, we don't do watches either, just like radiation storms. And the reason we don't do watches for flares and radiation storms, even though we're forecasting them, is because we're in solar maximum. We could have the watches out for day after day after day, and that does nobody any good. So we do warnings. For the flares, we don't do a warning because we don't have that capability, but we send out an alert at the R2 level, or what we call an M5 flare. So the R2 or greater, and then we'll summarize it. So that's what we put out. So the alert means it's happened, the warning means it's imminent, and the watch means the threat is there enough to warrant a watch.
Perfect. So I'm going to ask you this. What is one thing that you wish people knew a little bit more about space weather?
I wish they knew exactly what a coronal mass ejection was, or what a solar flare was, or what a particle radiation storm is, because we have these questions all the time. Fortunately, you put out a tornado warning, you don't have to tell people what a tornado is, right?
Right.
They know what a tornado is. We have that problem in space weather. And the other part of the problem is it normally will not affect people directly. I mean, you're not going to be hurt by these events as long as you could be on Mount Everest and you're not going to hurt by these events. The atmosphere and our magnetic barrier helps us, but it's our technology that can be impacted. And to the extent of that impact, then people could be much more directly affected, such as a wide-scale blackout or your GPS precision system that you need to get some work done or respond to an emergency in a crisis, and you're not accurate. That's a problem. Those impacts we can all feel, but they're not really a threat directly to your life or property. So that's kind of the thing I want people to know. And why it's important is because there's people out there that are controlling these things that we all rely upon, whether we know it or not. And it's up to them to
Right.
manage and mitigate it through the information we provide. And everybody else should just be space weather aware by visiting our webpage, spaceweather.gov, and through shows like you're doing today.
That was going to be my next question was where they could go. Do you guys also have like any YouTube videos, or is it just kind of on your website where they could learn a little bit more about this?
Yeah, we do have education outreach material on our page. There's a bunch of stuff about these phenomena, CMEs, sunspots, solar flares. People should go there and read for themselves more about these phenomena and what they mean so they understand them better when something happens. We are on social. We have our webpage, spaceweather.gov. We have our social media. We have a Twitter and Facebook account at NWS SWPC. And also in the most recent event, we tried something new. And that was trying to get a video out there during the event. It's not a YouTube channel, but it was just a video that we posted out there on social media on those platforms.
That's how we found you. Yeah.
Yeah. And that was me walking around with a laptop in my hand trying to do it because we don't have the materials yet, but we're ordering them now because that was very successful. People really responded very positively, and they were grateful that we did something like that because they know that we're the nation's expert when it comes to space weather. And we want them to come to us, and we're happy to do that more for future significant events.
Perfect. Well, we have about 1 minute left. Is there any final message that you would like to give to the viewers before you head out?
I think we've covered it really well, Nathan. I just hope people take advantage of our webpage, go explore for yourself. You can monitor space weather conditions for yourself when you learn more about it and know exactly, hey, this is favorable now because of what I learned on SWPC's webpage and from a show like yours for me to drive out 30 minutes out of town and look for the aurora because I'm probably going to see it, as opposed to, no, this isn't looking favorable.
Right. Well, we thank you very much for taking the time to come and join us today. I think not only did I learn a lot, but a lot of people at home probably learned quite a bit as well. So thank you, Shawn, again for coming and talking to us and letting us learn a little bit more.
Hey, you're welcome, Nathan. Thanks for having us. Anytime.
All right. Thank you. We'll see you guys again at the same time tomorrow here on Storm Team 5 Plus.